can you share your slides, please?
Hello, sir.
Yeah, can you share your slides, please? Yeah.
Am I audible?
Yeah, you are. We can hear you clearly.
Okay, thank you.
We can't see your slides yet, but we're imagining we will see them soon. So
my slides are visible?
yep, just if you can go to full screen, that would be awesome.
Yes.
And then we can hear you, and please start.
Is it fine, sir?
It's perfect. Yeah, please start.
Yeah. Hello, everyone. Myself, Santanu Kumar Das, working under the supervision of Professor Santanu Kole and in the Department of Mathematics at Birla Institute of Technology and Science, Pilani, Hyderabad campus. So the title of my talk is Viscoelastic Membrane Dynamics, the Influence of Bathymetry on Random Wave Conditions. As we know that protection of the shore and from the high amplitude waves as well as the onshore protection, leading to a concrete idea among the ocean engineers and the engineers to recommend to build a kind of structure that can adhere to the protection of the shorelines from this degradation of this what you call near shore regions. And to do this, several kind of structures have been designed, implemented, and but the recent trend is that the problem with this kind of very large structure is that the coastal economy as well as the financial that need to be bear by the government across the countries to build this kind of structures, which are actually very expensive in nature to build in the near shore regions. So in this regard, floating membranes are some flexible kind of structures that are made of materials such as reinforced rubber, geotextile fibers, plastics that are widely used in the offshore and the coastal engineering applications. The main idea is not to completely abolish this breakwater kind of structure, but the idea behind is that these are lightweight, easily deployable, reusable, and have the we can use whenever it is required, and we can move from one location to another location as per the requirement. So in this present study, we have considered the viscoelastic membrane, and these are the outlines of my presentation. Initially, I will talking about the introduction and the motivation of our problem, and then we will be using the mathematical formulation, and following the solution methodology, we will discuss the key results associated with this study. So the viscoelastic membranes are thin, flexible materials that exhibits both elastic and viscous behavior under stress. And one of the key advantages that it can deform instantly like an elastic material, and also it helps us to dissipate the energy over like a viscous fluid. In terms of in this present context, we have the viscous elastic membrane has been modeled as a thin, deformable nature of structure, and for the applications of the offshore engineering, including wave energy harvesting and the marine structures related things, the understanding this kind of structures is highly uh, valuable to the ocean engineering backgrounds. And it is observed that while the bathymetry, the variable bottom foundations in any kind of structures plays a crucial role. If you look at the wave energy converter device also, Rangier is the one whose pioneer work has been tells us that the introduction of the artificial bottom profile near shore the environment can significantly enhance the wave energy capture ratio through the OWC device kind of thing. Also, there are so many previous literature studies have been done which can demonstrate that the bathymetry plays a crucial role in enhancing and to know the real engineering applications for this kind of structures. So, and regarding this random wave conditions, often we feel look at the ocean, these are not actually in the regular waves pattern that we consider for maximum kind of studies. In general, these are highly irregular in nature, and this can be represented by a suitable what we call the spectral analysis as provided that the random wave conditions can be represented by some suitable C spectrum. So in this present study, we will study on the bathymetry effect as well as the random wave conditions by considering the Pierson-Moskowitz. And besides that, we will discuss the hydrodynamic parameters associated with these random waves, how they behave over a time and over the change with the angular frequency. And I hope this is like not a complete work. I am still doing, but I hope these findings can get a theoretical framework and practical significance in the marine membranes and enhancing their performance in the unpredictable wave environments. So this is the schematic view of the sorry for the caption. And this is the membrane that is placed over a variable bathymetry. And to model this, we have used the linear water wave theory, and the assumptions are taken to be the fluid is assumed to be incompressible and viscous, and the flow is assumed to be rotational. And the problem has been studied with the help of the suitable two-dimensional Cartesian coordinate framework. The small amplitude water wave theory has been considered, and the motion is considered to be simple harmonic in respect to time with the angular frequency omega. Due to this assumption of this incompressible and inviscous, irrotational, there exists a velocity potential of this form, where it's the spatial potential function phi satisfies this governing equation, and the bottom boundary condition through where actually we have considered that it is a residing permeable structure. So there will be no flow across the bottom. So the boundary condition is given by equation number 2, and the bottom boundary is given by stated in the equation number 3, which is taken from a well-established paper, and it represents a variable bathymetry. And these are actually two types. If you consider this the end term delta SC, this actually if you take it as 0, it's look like a shoal kind of bottom. And if you go for consider like type 2, it will be like a undulated kind of thing, and there will be no uniformity across this true boundary. And the free surface boundary conditions, excluding that membrane part, it will satisfy this equation number 5, and assume to be the membrane to be flexible and uniform in the longitude direction. The membrane's reflection can be expressed using equation 6, and the kinematic equations of the membrane is given by equation number 7, and the membrane dynamic boundary condition is given by equation number 8, where T is the membrane's tension with having the expressions, and tau is the damping parameter of the membrane. And it is to be noted that if it is 0, then it behaves like a rigid plate. And for this present analysis, we have considered the edge to be fixed. That implies that the edge conditions are taken to be 0 at the corner of the membrane in the boundary gamma m. And the far-field boundary conditions are given by equation number 10, where this K0 and P0 are associated with the positive real root of the dispersion relations and for the corresponding water depth. Now, to solve this kind of problem, we have employed the numerical technique, because the problem that we have seen in the schematic diagram doesn't look like a regular kind of structure. So in this realm, the adoption of this numerical techniques are actually comfortably can handle this kind of structures. And why boundary element method is because rather than this finite element method and finite difference method, the boundary element method itself reduces the dimensionality of the problem, because the whole thing, the entire computation is carried out only over the boundary, which itself reduces the dimensionality of the problem. And and it is considerably one of the efficient. Unlike the finite element method, if you look at the finite element method, it needs the discretization over the entire domain, which seems to be very time consumable. And the why it is coupled with the finite difference method is to effectively handle the membrane dynamic condition that is given by second order. And for the further studies like the higher order equations like fourth order and fifth order, it can suitably merge to handle with the boundary element method. And one of the disadvantages is that it can seems to be like the interface problem. Unlike just like if we have a multi-regions, then at the interface we can have a problem. And the boundary element method, unlike the finite element method, is fully populated. So that's lead to a singularity sometimes. And it is also sometimes it is found that it cannot handle the non-linearity, just like FEM. So to do the boundary element method, initially the green second identity is used over the potential function and suitable fundamental solution. The fundamental solution satisfies the governing equation, only the Laplace equation, not the boundary conditions, which on incorporating we get the Freedom integral equations of second kind as given in equation number 12, where this xi and eta represent the field and source point. And this physically represent the effect of this fundamental solution represent the effect of this field point due to this unit source. And implementing all the boundary conditions as we have mentioned in the free surface boundary condition, the far field boundary condition, we get this equation number 13. And once the Freedom integral equations of second kind are formed, then the next step in the boundary element method is to discretize. So what we do in this kind of structure is like we do the partition of each of the boundary into a smaller number of finite segments and known as the boundary elements. And over each such boundary elements, the nodes are kept at the midpoint of the boundary elements and over which each of the source points runs. And as much time it depends like how much number of elements we have discretized. Based on that, the matrix are formed and it can be solved. And the advantage of this incorporating finite difference method is that we can discretize the membrane boundary condition as given number in 15. And this Hij and Gij are known as the influence coefficient. And these are basically the integration of the fundamental solutions. That is associated with the governing equations and are handled using the analytical and numerically based on the Gauss quadrature rule, which can effectively handle the singularity at the sharp corner as well as the what you call in the infinite domain. Now, for the present study, to analyze the effect of the random waves, we have considered one of the the fully developed and developed system, that is the Pierson-Moskowitz C spectrum. The idea of the original of the Pierson-Moskowitz C spectrum is that the assumption is that if the wind that blew steadily for a long time over a large area, the waves would come into an equilibrium with the wind. This is the concept of fully developed sea. And here, after a long time is roughly taken to ensure the representation. Several representation has been done. The initial representation was actually taken from the Phillips constant, and later on to effectively incorporate this significant wave height as well as the significant the corresponding wave period has been taken. And for the present situation, I have incorporated the JONSWAP spectrum, but due to the limitation of the time, I have not input the results. But the JONSWAP also is like an extension to the Pierson-Moskowitz, based on the assumption that the sea actually cannot be, the oceans cannot be treated as like a fully developed, never cannot be considered as a never fully developed. It continues to develop through the nonlinear water-wave interaction even for a long times and distance. So that's why the representation is quite similar like to the Pierson-Moskowitz with a peak enhancement factor. However, if you look at this gamma, if you take gamma is equal to 1, it eventually transforms to the Pierson-Moskowitz itself. Now, while estimating this kind of structures, what we do is that we consider we plot this spectrum over a finite range. If you look at this figure, this is a schematic diagram of the Pierson-Moskowitz, and in the B it is a JONSWAP, and in the C the comparison between the Pierson and Moskowitz, and in the D it is a Pierson-Moskowitz and JONSWAP for gamma is equal to 1. If you look at D, it's eventually show that for the peak enhancement factor, if you take gamma is equal to 1, it eventually transforms to Pierson-Moskowitz. However, if you look at the the comparison in the figure C, it shows that the JONSWAP is highly sharp, demonstrating that the C can behave more rough. And actually, if you look at this we have considered three suitable sea states to represent this spectrum. What we're gonna do is that, like, how we estimate this parameter is that we plot this like spectrum first, and we initially found the cutoff range where the entire energy is well distributed. If you look at this figure, then it's a line between 0.5 to within 3, the like energy is distributed very nicely. So what we're gonna do is that we consider with this range only, and we compare we partition them into n equally divided component, which eventually behave like a regular component. And although we can generate a random waves by superimposing a number of sinusoidal waves having different phase and different what you call wavelength. And if you look at this, and then we what we're gonna do is we partition into a regular component of n bands, and then we compute the reflection transmission associated with each component. Then following the work of the Goda and this, we and Cole as well as Liu, we get find this equation number 18 and 19 representing the reflected and transmitted as well as the vertical spectral density relations. And this Kr, Kt, and Kd are eventually calculated by the regular wave component by given as equation number 20, 21, 22, 23. And here this HI contain the square root of 8n0, like this is the root mean square. This is the expression for the wave height associated with the regular component, and in that is the statistically represent the what you call the variance. And based on this, we have found some results by varying the length of the membrane, the damping parameter, as well as the bathymetry effect. For the consider the Pierson spectrum, this is for the C state one. This figure represents the variation of this reflected, transmitted, dissipated, as well as the vertical force for the each of the individual component as plotted against the average angular frequency. And as we can see there, sinusoidal increasing and decreasing pattern has been shown in the Kr and Kt component. And we can see that as the value of this length of the membrane increase, the reflection effectively decrease for the each of the regular component, and it's a simultaneously increase for the dissipation. As we see that if you consider a long thin viscoelastic membrane with suitable like damping parameter, then it can effectively trap the wave energy associated from the random waves. And to validate this kind of things, like how this pattern is going to look and how it is behaving in this manner, we can see the spectral representation of the Pierson-Moskowitz for the length of the membrane. As you can see that for the reflected spectrum, the spectral like model, if you see as the length increase, it eventually decrease, and for the dissipation, it increase with the higher values of the length of the membrane. And the force itself, it is showing that the vertical force will be more, and eventually it decreases for the higher values. And this is the findings associated with the regular component for the damping parameter. As I told that if you take the value tau is equal to 0, it behaves like a rigid structure. Therefore, for tau is equal to 0, the peaks are of high amplitude in case of the reflection transmission. But as you can see that there will be no dissipation. This ensure that how this membrane behave for this higher values of this membrane. So to effectively work, we need to know like which kind like what kind of how much what we can say that like it should be porous kind of structure should be made. Like it should not be like more porous like that. It will eventually dissipate all these things. And if you look at the force parameter associated with the each regular component, it can be seen that for higher damping values, the vertical force is comparatively low. So it is always prefer that the damping parameters should have a good range to effectively dissipate the energy from the random waves. And to effectively understand how that works, the reflector spectrum, the transmitter spectrum, the dissipator spectrum, and the vertical force spectrum can be seen here. As we see that for the tau is equal to 0, the force associated with the viscoelastic membrane is comparatively higher compared to the tau is equal to 0.50, which is very less compared to the tau is equal to 0. And this is associated with the C state 3. If you look at the variations, here the like the values of this force is higher comparative to the C state 1. The reason behind is that when we consider higher C states, the effective energy distribution associated with this what you call this Pierson-Moskowitz spectrum, as seen in this figure, you can see that the energy distribution is comparatively higher compared to the C state 1. So as a result, more energy is distributed over that range. So as a consequence, when we plot for individual component, it will be higher for the higher C state values. So understanding the dynamics in the higher C states values is always predominantly actually needed, because in the real ocean scenario, we don't have any like the very low significant wave height to the wave probable period. And this is the findings associated with the damping parameter for the C state 3. If you look, the vertical force spectrum is associated with this Pierson-Moskowitz spectrum is comparatively higher in the range of the initial 0.5 to 1. Why? Because is that? Because if you look at the spectral figure, you can see that within the range of 0.5 to 1.5, the distributions of this C state 3 is higher compared to the 1. And in that region, the peak distributions is there. So as a result, the comparatively the spectral distribution is higher for the higher C states. And whatever, if we look at this zones of spectrum, it will be eventually more larger than the Pierson-Moskowitz. So for the real case also, because if you just look at the comparison as I provided in figure C, JONSWAP is comparatively that peak enhancement factor make it as a narrow banded spectrum kind of thing, where for a short duration the impact of this like the waves will be higher within this range of this omega. And these are the finding associated with the length of the membrane for C state 3. And effectively we can see for C state 3 also, as the values of the length of the membrane increase, it significantly increase for a short duration, then it significantly decrease due to the enhancement of the dissipations. And the vertical force spectrum is clearly shown in this figure. And the bottom profile associated with, we have considered the undulations like that. The bottom profile we have considered actually for the all other studies we have considered the value R minus L, that is divided by 2 to like it will appear like the bottom undulation is completely lie beneath the membrane itself. But we have considered the cases where the undulation will start before the membrane or after the end of the membrane, or at the location of 0, which will be shifted toward the left or right of the membrane. So this kind of structure is like necessary to like how in the, like under which conditions it behaves very nicely. So the reflected spectrum shows that like for the if you move towards the right, actually we can see that the like the impact is actually high for the reflector spectrum as well as the vertical force spectrum. So it's better that to like facilitate the this kind of structure in the real scenario ocean. So it should be effectively kept under the membrane so that it can effectively behave. So these are some of my reference. Thank you for your attention.
Thank you very much. You know, keeping to time very well, as all the speakers have. Is there any questions for Santanu?
Yeah, I would like to ask a question. Probably I missed, but could you show please again what is the model for dissipation in the membrane?
For the present time, we have computed dissipation for the we have taken by 1 minus kr square minus kt square. But the explicit
show us the equations of motion, the original equations.
Yes, I have the we have derived that, but for the present time, I have not incorporated this original expressions. It has been given. Yes.
Where are your boundary, the initial conditions of your problem?
Yes.
So what we can see here.
Where's the condition for the membrane?
Yeah, is equation number 7 is for the linearized kinematic boundary conditions, and for 8 it is dynamic boundary conditions.
So which term is responsible for the dissipation?
This damping parameter associated with the membrane.
Where's that?
Yes, it's
okay. So the T has a imaginary part.
Yes.
T is membrane tension.
So go back here. Yeah, you can see it there, and that's the time derivative, exactly like we had in that other expression.
Yes, sir.
Yeah. Okay. I'm starting to make sense now. So that adds an imaginary part to the T. Yeah.
Yes.
Which is what.
And did you discover any effect of dissipation on your calculation, on your results?
I'm sorry, sir, I didn't get. Can you repeat it?
Did you discover any significant influence of dissipation on your results?
Yes. Like it's completely depend upon the how it the present study requires a fine tune of the damping parameter as well as the bathymetry effect. But together that only we can decide under which circumstance it can behave very nicely. So few of the results, if you can see here, these are the results associated with the what you call dissipations for the length of the membrane. You can see here.
Okay, thank you.
Yes.
I find it just a comment about the spectrum, because if you went out and you went to the ocean,
Yes, sir.
And you measured the wave spectrum,
yes, sir,
it would never be the Pierson-Moskowitz spectrum. You would never find that, and you'd never find the JONSWAP spectrum anywhere. They don't exist in the ocean. Because they're a random process, so they're always different.
Yes.
And there are swells that are coming from storms that are propagated a long way, and so in a sense, I'm not sure how much I would worry about these different. Like if you go back, if you show the spectrum,
yes, this.
So I think the JONSWAP spectrum is 50 years old or something, and there's a reason no one's come up with a better one, because it would you sort of can't, since it's a random process.
Yes.
Whatever you say is going to be quickly proven it's wrong. So in a way, I don't know how much profit there is. I mean, if you're in a real situation, that the wave spectrum, say even average wave spectrum off the coast of Mumbai, would have a very distinct character to it.
Yeah, that's true, sir. Absolutely. But with the recent idea, like these are for the narrow banded spectrum, we assume that this follow an ergodic process as well as this what we call Gaussian. But if you consider the wide band, it follows actually Rayleigh distributions. And for that, the recent studies have been DNB spectrum is one of such kind of thing which follows the Rayleigh distributions, and it incorporates the current as well as wave current induced effect also. Recently I started with that work with one paper. So yeah, it's a natural that obviously that we can't find actually the narrow banded spectrum to be really applicable. So
no, it's, I mean, you've got to do something. You've got to choose something. Yeah.
Yes. But one of the recent find that I've found is that the DNB spectrum that follows actually the wide band. And
also it's sort of clear that there are these resonance of the system, those oscillating peaks. You could see them, sorry, in that previous slide. Yeah.
Yes.
Like these frequencies that waves are bouncing up and down the membrane. I think though we should very interesting, and thank you very much for the talk.
Yeah,
It was another great talk. Okay,
thank you,
you're
sir.
doing great work. So we're going to move on to what isn't